Hello and good afternoon. This is Peter Gregory, and I'm going to give you an explanation of the example in the Jacobs book, Chapter 4 of the time cost study with the critical path model. Okay, so I'm in Lucid Chart here, and I've drawn a couple of slides that I put into PowerPoint and I've put up on the internet on eClass. So each class, each section has access to an enhanced PowerPoint from the last time we talked about this example. A few students came to me with some questions, and so I created the video here to address some of the questions about how the results were arrived at regarding that example of the critical path in Jacob's book. Okay, so I'm in Lucid Chart. I started out with a blank sheet, and then I created within my one document here, I created multiple sheets. And as we go along here, if I show you a few things about Lucid Chart, maybe it will help you. As you see along the top, we have different tabs. I've created a number of sheets that reflect the cycles that we're in. There's the different cycles regarding the critical path analysis that we did. I've created a sheet to show progressively as we go through this and we shave a day off one by one where we start with. So starting with a blank sheet here, we'll click on cycle 0. This is the starting point, and this is a diagram of the network that we have. And what I've done here is put in the early start, early finish times, and the late start, late finish times. Okay. I'm going to flip over here to the PowerPoint to show that I've added these slides in there with maybe even a little bit more explanation. So let's run our slideshow here from the beginning. So in the slides, this is the problem, statement of the problem. Procedure for project crashing consists of the following 5 steps. Is explained by using the simple 4-activity network shown in Exhibit 4.8 and assume direct costs are $10 per day, indirect costs are $10 per day for the first 8 days, and once it goes past 8 days, the indirect goes to $15, or as stated here, it increases by 5. We don't really touch on that until we get into class tomorrow and Wednesday. But here we go. I'm going to show you a little progressive here about how this problem is worked out, okay? So this is the statement, this is the example out of the book, the drawing out of the book, shows the network. And as you can see, we have our normal times and our crash times above the activity. And we have the normal cost and the crash cost below there. Now these numbers, if you look at it, the numbers on the cost are actually the cost of the entire activity. So under our normal time of 2 days for activity A, it costs us $6. Since it takes 2 days, we spread $6 out over 2 days, and that averages out to $3 a day. Okay, so that's how the problem is stated. Make sure you understand that the entire process of A for 2 days is costs $6. Okay, and so the numbers are. This is just a given. These are just the given numbers here, with the normal cost of 6 and the rush cost or the crash cost of $10 a day. That's the difference. Okay. So the first thing to do, shown down below here, is create your network, and that is what I created in Lucid Chart. And when you first create your network, just use your nominal times. The normal time for A is 2, the normal time for B is 5, normal time for C is 4, and the normal time for D is 3. And when we work through the early start times, we start at time 0, we add our A of 2, we finish at the second day. So the early finishes from one activity is the early start on the next activity. So we start with 2 plus the 5 is 7. The next activity starts on day 7, goes for 3 days, and ends on day 10. So that's just a repeat of the problem. This is the table, some of which you should put into the Excel sheet, and it shows some of the equations involved here. Because when we do our problem, we want to find out, we don't want absolute how much does it cost every day, but what's the difference? How much extra does it cost us every day? The problem is stated in such a way that we'd like to be aware of what happens with the increase of speed to the process or the reduction of time per day. For instance, in activity A, crash cost minus the normal cost is $4 over the period that it applies. And the period that applies is your normal time minus the crash time. So you subtract the normal time of 2, you subtract the 1, and the difference is 1 day. So to speed up 1 day, it costs us $4. Here's the relationship just shown. This column here is just crash cost minus normal cost over normal time minus crash time. Okay, so we can just calculate that out. You should be doing that in Excel, and you come out to $4 a day. Something else they're telling us is that you only can save 1 day in activity A, whereas you can save 3 days in activity B, and 1 day in activity C, and 2 days in activity D. The lower part of the chart, as we went over, shows when you start with the nominal time through there of 10 days, how much it costs is 26. And I'm going to show you where that comes from because we didn't talk about that. I'm going to show you where that is calculated from. And then we're going to step through this using our network, and I'm going to update the numbers as we go along, and you'll see how the entire system, you'd really want to represent it and probably write a piece of software, use a piece of software to represent all the cycles. So what we're looking at here is cycle 0 is the normal time that it takes to go through the system. The top line is 10 days, $26. Okay, I'm going to flip over to our PowerPoint here. And look at, focus on what's going on here. This is just reproduced, the network that we've reproduced. This is the network we've reproduced here. And it has just the early starts and the late starts, has all the numbers in right from the book. Okay, so this comes right from the book. But what I wanted to do is show in this slide, I wanted to show where the cost of $26 comes from. Okay, if you go back to the original information that was given to us, if you look at the normal cost for A for 2 days was $6, the normal cost for B was $9, the normal cost for C is $6, the normal cost for D is $5. Take a look at those numbers, and then when we come down here, we just apply them. I just put the 6 refers to activity A, the $9 refers to activity B, $5 to D, and $6 to C. These are the normal time. These are the costs to get through this whole system. And adding them all together, it comes out to 10 days. If you look at the entire cost to get through there in 10 days, it's just the 6 plus the 9 plus the 6 plus the 5. I'm stating that down here in the yellow box. Total normal time cost of process, so the normal time of 10 days, cost of the process is those numbers added up, and it comes out to $26. So that's where the number in the table comes from. I wanted to show that in this first slide. Okay, I'm going to go back over to our Lucid chart. This is where all the original drawings are from, but I'd overlaid some information in PowerPoint about those costs. What I did was I annotated the drawing or the network diagram with how many dollars per day it costs to speed up the process for each of these activities. So it's $4 for A, 3 for B, 2 for C, and 2 for D. And if you remember, we're trying to find the cheapest way to knock a day at a time off. The approach to the problem is start at 10 days, work backwards, and subtract the cheapest day to buy a shortened process. Every time you shorten by a day, you're looking for the cheapest place to buy that from. And when we first look at the numbers, we know A is the most expensive, B is the next, and then C and D come in at the cheapest. They're both $2. And we have to do some analysis to figure out why that is. I'm going to make a little correction here. So that this 3 should not be X'd out. I just wanted to fix that. It comes from a little bit of other work that I did. So there we go. So that looks better. If you go through this network, it takes 2 days to get through A. That's the 0 to 2. Starting at the second day, takes 5 days to get through B. That's to the 7. 2 plus 5 is 7. And then D starts on the 7th day and takes 3 days and ends on the 10th day. Okay. If we go through the southern route here, you're going to see you start on the day 0, takes you to day 2. Day 2, we start the C process, and there's 4 days there, so 2 plus 4 is 6. And we recognize, comparing these numbers, that at the early finish to the early start here, this is the early finish down here, early start up here, there's an extra day that's going to amount to some slack time, possible slack time. We're not really concerned. Here's a big point. We're not really concerned with slack in this problem. We're trying to bring all the processes to the beginning date, keep them as close to the beginning date or start as early as possible here, and look for opportunities to buy a day here, buy a day there, and shorten the entire process up for our customer. The first thing we do is that now I'm going to the next page. You can see I just typed the next tab, and what I've basically done is just copied one page over and over and over again here and added information to it. You're going to see where we added information. I want to do this a little bit slowly. Okay, I think there might have been some question about this. All right. So when we look at the network and we look where we can buy time from, the first place we're going to look to see is if we can spend only $2 and buy a day. Okay. The reason we're not going to pick C is because there's a slack time in here. We'd be buying a fruitless day. We buy a day here at C, and yet overall it wouldn't impact the total time through the system. Our critical path, you're looking for things on the critical path you can reduce. C isn't on the critical path, and even though it's 2, the logic and the reasoning behind this is to get something off the critical path here. So what we do is we spend $2, we shorten a day on D, and you can see I crossed out the 3. Now we're going to do it in 2 days, and it affects the only other numbers really that get changed in the whole system are at the tail end here, the early finish and the late finish, which will be the same on the critical path. Okay, so that's where we bought our day. There's the 9 that shows up in the table. That's the 9 that shows up here. So we're taking a look at the bubble diagram, and now we're taking a look at their chart. We had cost $2, went from 26 to 28, cost $2. We saved a day at D. That's what this chart is telling us. So now where do we get our next day savings from? We're looking for the next place to buy a day. Well, because no other numbers really changed, we have at least a couple days available we can buy at D. So there's another day available at D for $2. So what we're going to do, the next chart's going to show we buy another day from D for $2. And I'm going to show you that a little bit more clearly. So that's where we were. We had shaved it down to 2 days, and now we're going to shave it down to 1 day. Take another day off there, and notice our finish time came in by a day. Now we're down to 8 days. That's the 8 in this chart here. That's how we got it. And that's how it looks. This is how it looks in the lucid chart. This is if you're keeping track at home. This is like scoring at home, and I'm keeping track now of what happened. So we saved a day, then another day on D, and we're down to 8 days. Okay. So now where do we go? The issue is that D, we were only able to buy 2 days. There's the 2 days right there. We already used them up. That's over with. We've expended anything we can from D. We've got to find another place. So going back to our chart, we wouldn't use C because B is still the longest element in the critical path. There's still an issue here where it goes beyond the finish time here, goes beyond the finish time of C. Finish time of B goes beyond finish time of C. So we're going to take a look at B. Maybe we can buy something there for $3. Now it's going to cost us $3 to buy a day there versus $4 for A. If the numbers were different, we might be looking at A. We may shorten it there, but it's more expensive to buy it from A. We'd have to buy it for $4. So we have to go to B. So just out of interest, let's take a look at our chart up here. B actually has 3 days we can buy from the process there at $3 a day. So going back to our chart here, we're going to use B to shorten up the process. Well, the table is clear. Your bubble diagram starts getting a little more complicated, and that's why I removed the arrows. Just understood that the arrows are here. I took them off the diagram because it's starting to get a little bit complex. What happens is when you start reducing the duration of inner activities, when you save a day, it trickles through other activities, and all these numbers have to change. So that's where you'd want a system, like a software system, to be able to operate this, but I'm going to do it somewhat manually here. So the next item is we're going to take a day off of B and pay $3 for it. Again, back in our chart, this is where we are. We bought 2 days from D, and now we're going to buy one for B. We paid another $3. See, we're paying more and more as time goes on to buy these days, and it's accumulating. So now we're up to trying to save the 3rd day, and it's costing us a $3 on that day. Going back to the diagram here, I'm going to move to the next picture. And to simplify so we don't hurt our eyes here, I covered up D because there's a trickle effect. It ripples through the entire network when we change a date on the inner part of the network. All the numbers have to trickle through, propagate through. Okay. But the nomenclature here, you can see, is an activity B started out at 5 days. We took one day off, so that's exactly what we're doing. We're finishing up a day early. So instead of 7 days, we're finishing on 6, and we paid $3 for that. Going back to the table, just to reinforce that, there we are. We paid $3. We bought a day from B, and this is what happens. If you take a look underneath the expended D, this is what's happening. It's a little bit complicated, and I will show it here, but you can see that the day has to ripple through. We've saved a day here, and the finish day is now 7. And that's why I wanted to show a dynamic view of this, because the changes are rippling through the system now that we're working on activities more internal to the process. Okay, but I cover this up so we don't hurt our eyes on that. It gets a little complicated there. Where do we go next? Where do we buy our next day? One of the things to note, coming back to the drawing, at the same cycle we're on, you'll notice the finish date of B now aligns with the finish date of C. The early finish time of C at 6 is aligning with the finish times of B. That means we have to move both of these. We have to buy a day, if they're available, from one from B and one from C. We have to move these together to move this back. So when we save a day, we're now only taking 5 days through this point of the network. If you're going to do that, you have to add it up the $3 for the day for B and the $2 for the day of C, and that comes out to $5. So it costs $5 to move both of these in tandem back one day, or shorten them up by one day. The alternative is to go back to A. We look at A, it only costs $4 to buy a day at A. Let's go back to the table. Let's take a look at what that looks like. Okay, so this is a decision point. We have to decide whether to move B and C or A. And the answer is going to be A because it's cheaper. So we go back and what does it look like in the chart? Okay, so this is the point where some explanation comes in the book where they asterisk the solution, because now they're explaining what I just mentioned here, is that you have to make a decision. It's decision time. It costs us $4 to buy a day from A. There's 33 plus 4 is 37. And we've reduced the overall time in the network from 7 to 6 days. Okay, so we're always looking for the next cheapest alternative, and in this case it was A. Let's take a look at what that looks like. Okay, I took a little break there. Continuing where we were, we're showing that we're going to target A to buy save a day at $4 a day versus the combined cost of B and C at $5. That's 3 plus 2 is 5 to reduce these two activities by one day. They're all finishing at 6 at this point. You see C and B are finishing at 6 days. We'd have to save a day, we'd have to buy a day from each of those. So that'd be 3 plus 5 versus buying one day at A for $4. Okay. So the next diagram to show there is ignoring the details, the gory details underneath the cover here of what happens in the rest of the network. This just shows simply that we're buying the day from A, we reduce it from 2 weeks or 2 days to one day, and we adjust all the areas that need to be adjusted on this. And if you really want to see what would trickle through or propagate through the system, we'll take the cover off this for a second, and we'll see that because we struck a day here, we have to strike a day. We have to show that we struck a day through all the rest of the activities. The day savings was at A, but because we're finishing on day 1 instead of 2, all the times change in the network because everybody gets to start earlier now that we bought a day from A. Okay, and you can see why I put the cover over there, because a lot of detail, whether you want to see it or not. You could stop the video there and take a look at those numbers, but I basically showed how we saved the time. You can see all the strike throughs. We have to keep changing those down. Okay, so you can take a look at that if you care to. You don't have to. Okay, let's go back to our table now. So going back to our table, we see on our line there's the A. That's the day that we saved at A, and we're now only taking 6 days. We had to pay $4, so 33 plus 4 is 37. Just want to show something under the cover again. So here we are back here. And we're talking about the whole process taking 6 days. There's your 6 days at the very end. You just want to make sure things are correct. Okay. All right, let's cover that up. Okay, let's take a look at the next area that we can save a day. Now what are we going to do? Well, if you go to your charts, you're only able to save 1 day at A, and we just spent our money to save that day. We now have none left there. Our other alternative was to shorten the process by moving both B and C at the same time, and that's what we're going to have to do. It's our current option, our current best option. So fix this here. Where A is expended and D is expended, we've done everything we can on A and D. We have to look at B and C. We already went through this a little bit. It's going to cost us $5 to save a day. Okay, and that's what we do in this diagram. We save a day by buying a B and a C. Okay, so there we go. So the next step is we have to buy a B and a C. It costs us $5 extra for that day, so it's 37 plus 5 is 42. And we now are down at about the minimum that we can get. The total process, the shortest we can go to is 5 days, because we're only able to buy the last step. We bought the only available day we could buy from C. So we paid $2 for C. There's nowhere to shorten C up anymore. Okay. The only thing left in the system is we can't shorten the overall time in the system, but we could possibly, because we have 1 day left on B, we could possibly shorten B up. And the only reason to do that, to spend the money on it, is for probability reason, is that the probability of something going wrong. If you hold off B to the last minute, where you have, what you'll find is you have a week of decision there. You don't have to start for another day. Another day. But the thing is to reduce the probability of, or the risk of something going wrong, is sometimes you want to start a process as early as possible, just to hedge and make sure nothing goes wrong with that process. That'd be the only reason to spend another $3 and bring B in. And if you can't pass the cost on to your client, you probably wouldn't do it. Okay? So that's a little bit of an explanation, and I hope that helps with the problem from Chapter 4 of Jacobs a little bit more after I heard some questions from the class. Thanks very much.